Hello everyone, let us continue our discussion. We are in week 6 and this is lecture 2. In the previous lecture, we studied stress-strain relation, right? And for that, we started with generalized Hooke's law. And if you recall, in this generalized Hooke's law, we have 36 material constants, right? And our material was homogeneous, elastic, and isotropic, right? And for this isotropic case, we have two constants. So basically this 36 constants in the generalized Hooke's law, it reduces to two constants, and these two constants are lambda and mu. They are called Lami's constants. And with the help of these two constants, we can express Young's modulus, Poisson's ratio, bulk modulus, and shear modulus. If you recall the expression shear modulus, G is equal to mu, then K bulk modulus is equal to 3 lambda plus 2 mu divided by 3. Young's modulus is equal to mu times 3 lambda plus 2 mu divided by lambda plus mu. And the last one, Poisson's ratio, is equal to lambda divided by 2 times lambda plus mu. So you can see all of them, E, nu, K and G, we can express using Lami's constants. Now from your elementary strength of material, you know that you can also express the linear elastic isotropic material using E and nu. These are the two independent constants, and then using these two constants, we can actually express others. Today, we are going to investigate that further as we progress in this lecture. Okay. Now, for that, if you recall, how did we derive the bulk modulus? For bulk modulus, we actually derived the expression, if you recall, sigma 1 plus sigma 2 plus sigma 3 is equal to 3 lambda plus 2 mu times the volumetric strain delta. Then we applied a special case where sigma 1 is equal to sigma 2 is equal to sigma 3, and that is equal to P. That is the amount of pressure we apply along 3 directions, 1, 2, 3. These are the 3 principal directions, right? That means this P is equal to what? First invariant I1 by 3. Okay. Now, what is the definition of bulk modulus? K bulk modulus is equal to pressure divided by volumetric strain, right? That means it is P by delta. So now in place of P, we can write I1 by 3, right? And then in place of delta, what we can write, if you recall, it's the volumetric strain. So that means epsilon 1 plus epsilon 2 plus epsilon 3, right? Now, let us recall the expression of epsilon 1. Epsilon 1 is equal to 1 by E within bracket sigma 1 minus nu times sigma 2 plus sigma 3. Right? Similarly, we can also write down epsilon 2 is equal to 1 by E within bracket sigma 2 minus nu times sigma 3 plus sigma 1. And the last one, epsilon 3 is equal to 1 by E within bracket sigma 3 minus nu times sigma 1 plus sigma 2. Okay. Now if we add epsilon 1, epsilon 2, epsilon 3, on the left hand side we have the volumetric strain delta. So epsilon 1 plus epsilon 2 plus epsilon 3, this is equal to 1 by E. Then obviously the first term will be sigma 1 plus sigma 2 plus sigma 3, and that is our first invariant I1. Minus, we can take this new common, and you see within bracket we have twice sigma 1 plus sigma 2 plus sigma 3. So what we have effectively 2 times nu multiplied by first invariant I1, right? So if that is the case, then delta is equal to 1 by E and then I1 within bracket 1 minus 2 nu, right? So the expression for K is here I1 by 3 divided by delta. So if we evaluate what is K, is it I1 by 3 divided by delta. Now if we put the expression of delta here, so what we get is I1 by 3, and in place of delta we have 1 by E, then I1 multiplied by 1 minus 2 nu. Okay. So effectively what we get? K, that is bulk modulus, is equal to E divided by 3 times 1 minus 2 nu. Okay. So from this derivation, what we see is bulk modulus K you can express in terms of Young's modulus and Poisson's ratio. So it's not a independent constant, right? Now, if you carefully note that this denominator on the right hand side E is greater than 0, right? It is always positive. Okay. Also, bulk modulus is greater than 0. It can be equal to 0. That is the limiting case. Now, if that is the case, obviously, both of them, E and K, they are positive. And for that, we must have 1 minus 2 nu is greater than equal to 0. So if that is the case, 1 is greater than equal to 2 nu. That means nu is less than equal to half. That's the limiting value of Poisson's ratio. So that is one side of the limiting value. We'll see the other range in a minute, but for the time being, we get the maximum value of Poisson's ratio, and that is half or 0.5. So we'll always have Poisson's ratio less than 0.5. That's the limiting value, right? Okay. Now, let us see whether we can express G, that is shear modulus, in terms of E and nu. If we can express, then we can consider this Young's modulus and Poisson's ratio are the two independent constants. Just like we have lambda and mu, the lambda is constant. Then using this Young's modulus and Poisson's ratio, we can express other two constants. Bulk modulus we have already derived. So let us see what happens in case of shear modulus. For that, let us consider a 2D case. So we have a 2D problem under pure shear. So we have shear stress acting at the edges. So this is tau. Obviously complementary shears are equal. So we have tau on the other face. Now it will deform along the diagonal. So if we draw the deformed shape because of this state of pure shear, so we'll get this is the deformation. Let the sides be, say, A, and obviously the diagonal is square root of 2 times A, and this angle is 45 degree, right? Obviously this deformation is gamma times A. So let us focus the elongation along the diagonal, right? So for that, let us draw the diagonal. And for small strain, this angle is actually 45 degree plus or minus some variation. But because this is small strain, let us consider this also to be 45 degree, right? So let us drop a perpendicular. Obviously this distance is basically the elongation of the diagonal, right? So this we can find out. So it is gamma A times cos of 45 degree, right? So if that is the case, we can now find out the strain along the diagonal. So the strain along the diagonal is say gamma D. This is equal to the change in length, which is gamma A times cos of 45 degree over the original length, which is the root of 2 times A. So this is equal to gamma, that is the shear strain, divided by 2. Okay. Now, as per definition, shear modulus G is equal to tau, that is the shear stress, divided by gamma, that is the shear strain. Okay. Then we can express gamma D as tau divided by 2G, right? Okay. Now, as we have to correlate G with Young's modulus and Poisson's ratio, so let us consider an equivalent state of stress where we apply tension along this diagonal. So sigma 1 is equal to say tau, and then we apply a compression. Sigma 2 is equal to minus tau, right? Then what will happen? Obviously, we'll get a deformed shape, what we have already drawn using this red dotted line here, right? Okay. Now, if we focus on this second case, we can derive the elongation along the diagonal, right? Okay. So, for that, gamma d will be what? This is equal to sigma 1 divided by Young's modulus minus nu times sigma 2 divided by Young's modulus. So, if we put the expression of sigma 1, which is tau divided by E, then minus nu, and then sigma 2 is minus tau divided by E. So, effectively what we get? We get gamma d is equal to tau divided by Young's modulus E within bracket 1 plus nu. Now, we have already derived the expression of gamma d. So, if we equate these two, we have tau by 2g is equal to tau divided by Young's modulus E times 1 plus nu. Then we can cancel tau on either side, and effectively what we get, G is equal to E by 2 times 1 plus nu. So, what you can see is we have derived the expression for G in terms of E and nu, and earlier we have derived the expression for bulk modulus, which is here in terms of E and nu. That actually clarifies why we consider E and nu are the two independent constants, because with the help of these two, we can express bulk modulus and shear modulus. Now, let us focus on this expression of shear modulus, which is G is equal to E divided by 2 times 1 plus nu, right? Now, obviously, E is greater than 0. So, if E is greater than equal to 0, then obviously G is also greater than equal to 0. And for that, we'll have 1 plus nu, that is the denominator, it has to be greater than equal to 0. That means minus 1 is less than equal to. So, what we effectively get is minus 1 less than equal to nu is less than equal to half. So, that's the range of Poisson's ratio theoretically. So, this is the theoretical limit of Poisson's ratio, right? Remember, if this Poisson's ratio nu is equal to half, then what happens? You can evaluate the expression of this bulk modulus K the moment you put nu equal to half, so you'll have denominator 0. So you can imagine k is infinite. That means it is incompressible, right? Okay. So now let us quickly solve one example and then we will establish the relationship between stress and strain. Okay. For that, let us consider steel. Okay. So let us consider an example. So steel has Young's modulus E is equal to say 210 GPa and nu is equal to say 0.3. Okay. Our objective is to find out Lami's constant, lambda and mu. Okay. Now, if you recall, E is equal to mu times 3 lambda plus 2 mu divided by lambda plus mu. And Poisson's ratio nu is equal to lambda divided by lambda plus mu. Obviously, in our case, Young's modulus is 210 GPa, so we have 210 here, and Poisson's ratio is 0.3. Right. But from these two expressions, it's apparently difficult to find out lambda and mu. But for that, we have other clue. So let us first find out G, that is shear modulus. We have already derived here. So it is equal to E divided by 2 times 1 plus nu. So effectively it becomes 210 divided by 2 times 1 plus 0.3, right? And if you solve, the value of G is 80.77. Now recall, this is equal to mu. So one of the two Lami's constants we have evaluated, and that is 80.77. Now if you consider this second equation, so what we have, 0.3 is equal to lambda divided by lambda plus, in place of mu, we can write 80.77. And then if we solve this, our lambda is 34.62. So these are the two Lami's constants we get for steel having 210 GPa as the Young's modulus and 0.3 as the Poisson's ratio. And from this discussion, you can easily sense if we have elastic material, so we can easily find out from the stress strain behavior, uniaxial stress strain behavior, what is the Young's modulus, and we can also quantify Poisson's ratio. And the moment we quantify these two independent constants, we can estimate shear modulus and also bulk modulus, right? For this case, if you find out bulk modulus expression is 3 lambda plus 2 mu divided by 3, right? So the expression is 3 times 34.62 plus 2 times 80.77 divided by 3. So we have 88.47. Okay. So we have two independent constants, Young's modulus and Poisson's ratio. And we have also derived the theoretical limits of Poisson's ratio. And once we quantify Young's modulus and Poisson's ratio, then we can completely quantify the material property for a isotropic material, elastic homogeneous isotropic material, right? Okay, so now let us correlate stress and strain. So if you recall, we have already derived in the previous lecture tau x prime y prime is equal to g times gamma x prime y prime. In fact, we can now drop this prime. Similarly, we have tau yz is equal to g times gamma of yz, and then tau xz is equal to g times gamma z. So what we get from these three expressions? Shear stress is actually related to shear strain only, okay, for the material we are dealing with. Similarly, if we recall, epsilon xx is equal to what? 1 by E, within bracket we have sigma xx minus nu times sigma yy plus sigma zz, right? Similarly, epsilon yy is 1 by E within bracket sigma yy minus nu within bracket sigma zz plus sigma xx. And then epsilon zz is equal to 1 by E within bracket sigma zz minus nu times sigma xx plus sigma yy. Okay. Now we can correlate strains and stresses. So we have strain components epsilon xx, epsilon yy, and epsilon zz. Then gamma xy, gamma yz, and then finally gamma xz. Is equal to 1 by E within bracket. This will be 1 minus nu, then 0, 0, 0. And this is minus nu, 1 minus nu, 0, 0, 0. Then minus nu, 1, 0, 0, 0. Here we'll have zeros. And then fourth diagonal term is 2 times. If you recall the expression of G, we have already derived in terms of Young's modulus and Poisson's ratio. So we have 1 plus nu. Then 0, 0, 0, 2 into 1 plus nu, 0, 0, 0, 2 into 1 plus nu. Multiplied by the stress components, sigma xx, sigma yy, sigma zz, then tau xy, tau yz, tau xz. So this is the relation between strain and stress, and we have the constant that actually correlates strain and stress. And if you look at this 6 cross 6 matrix here, for this isotropic material, we have effectively Young's modulus and Poisson's ratio. These are the two independent constants. With the help of these two constants, we can construct the relationship between stress and strain. I hope that is clear to all of you. Just go through the derivations. And if you have any doubt, do let us know in our open sessions. We can discuss it further. Right? We'll have some problems for you. Try to solve it. If you have any difficulty, do let us know. We can clear your doubts. Thank you.